Hey guys, this is Javiman from Planting Seeds Tutoring. In this video, we're going to be discussing the light-dependent reactions of photosynthesis. Don't forget to use my referral code, JaviMon20, to receive 10% off your next tutoring package. Let's just start off with the basic definition for photosynthesis. It is a process that photoautotrophs, which are usually just plants, but it includes other organisms like cyanobacteria, and they utilize it. They use it to convert light energy to chemical energy. And notice that I said light energy and not necessarily solar energy. So this light energy can be from the sun. It's most of the time it's always going to be coming from the sun, but there are certain instances when you don't need the sun itself. The root of photosynthesis, the word photo comes from the Greek root, which means the Greek root for light. So that's light. And synthesis just means to create. So we have light to create, hence the name photosynthesis. Light creates food. Anyway, the commonly used chemical equation that we use to describe photosynthesis is C6CO2, which is carbon dioxide, plus 6H2O, which is water, with the help of sunlight, or any kind of light actually, yields C6H12O6, which is glucose. That's a sugar that we need for our day-to-day activities, plus 6O2. However, we're going to learn that this is not the entirety of photosynthesis. It's not this simple. Photosynthesis can be separated into two parts: the light-dependent reactions and the light-independent reactions. And the light-dependent reactions are called the light cycle. It's another name for it is the light cycle. And another couple of names for the light-independent reactions is the Calvin cycle or the dark reactions. We don't usually go with the dark reactions anymore. It's a more so old and out term, but we tend to always use Calvin cycle. And for today's session, we're just going to be looking at the light-dependent reactions. So the sun sends out a ton of electromagnetic radiation, which is another term for light, just a more sophisticated terminology, at all sorts of wavelengths. And some are just X-rays of about 2 nanometer lengths. And it sends up things like radio waves of up to 10 meters in wavelength. However, most of sunlight is emitted at about 300 nanometers and 1500 nanometers, with most of its intensity between about 390 to 700 nanometers, which is light, visible light. And we also see a lot of that's visible light. Everything that we can see is between 390 and 700 nanometers in wavelength. So since it also sends out between post 700 nanometers, between 700 and 1500, that's going to be your infrared region, the heat that we feel from the sun. And anything less than 390, well, we did say it's going to be between 300 and 1500. So 390 to 1500, that's about the UV radiation, which is pretty dangerous for us. Anyway, so if we zoom into the chloroplast of plant cells, there are things called thylakoids, which are small pancake-shaped sacs, which contain photosystems in their membranes that absorb this light from the sun. So right there, these pancake-shaped discs right there, that's going to be called the thylakoid. And this right here is an image, a close-up of how the membrane itself kind of looks like. So the stroma, that's going to be the stroma of the chloroplast, and the thylakoid, this is going to be the thylakoid lumen itself, the inside space of the thylakoid. So water, which is H2O right here, water molecules, which the plants get through their roots, are already inside this thylakoid lumen, and these H2O molecules are the providers of the electron flow that's needed to carry out the entirety of photosynthesis, at least the light-dependent reaction. So we can cross out H2O from this reaction since we just used it. We're using it right here. So that's how H2O is being used. So during the light-dependent reactions, photosystem II, so this figure right here, it sounds weird since it's named photosystem II, even though it's the first photosystem that's being used. It's called it because it was found after photosystem I. The scientists discovered it after photosystem I. Anyway, photosystem II has a reaction center known as P680, which is named because it's a group of pigments, hence the letter P, that absorb light at 680 nanometers at the prime. Anyway, so P680 is an extremely strong oxidizing agent, and it oxidizes H2O very well. Remember, when we say oxidizes, that means it's stealing its H2O. When it's getting oxidized, it's losing electrons. So the P680 pretty much takes away 2 electrons from the H2O, yielding 1/2 oxygen and 2 H+ ions. The oxygen molecules aren't needed anymore, and for the future processes, and so they just leave the plant. The oxygen itself just leaves the plant as byproducts through its stromata, which is also the same place that carbon dioxide comes into the plant for the Calvin cycle. So we're not going to be using carbon dioxide in any way whatsoever for the light-dependent reactions, and we already got the product of oxygen. So we kind of already solved part of the equation. Now the electrons enter into so we have 2 electrons right here, and it enters into the photosystem II, but it goes up due to because they are getting excited by a lot of energy from the sun, like from light energy. 680 nanometers light at a wavelength of 680 nanometers is hitting this photosystem II, which excites these 2 electrons, bringing them up to the very top. Now these electrons, to become less excited, they go through a series of a chain called the transport chain, the electron transport chain. And through this electron transport chain, when it goes through the cytochrome complex, it attracts H+ ions from the stroma, and it gets them to go down into the thylakoid lumen. So H+ goes down through the cytochrome complex into the thylakoid lumen. And we're going to see that the electrons just end up at the end of the electron transport chain. Now there are very low excitation states. They're not very energized or anything. However, we're also now at PS1, photosystem I. So photosystem I, like photosystem II, has a strong oxidizing agent, which is P700, and it pretty much deals in the 2 electrons. And photosystem I now is getting highly excited by a wavelength of about 700 nanometers, which excites the electrons to go back up. And these electrons, which are the same from earlier, are going to be used to reduce NADP plus NADP plus to NADPH. NADPH. So what happens is there's going to be a hydrogen that's also here, so it's a H+ ion. There's 2 positive charges up there, and we have 2 electrons. So both of these electrons just add up, and it yields a reaction, a combination reaction for NADPH, or synthesis reaction. Anyway, now that we have a lot of H+ in the thylakoid membrane, what happens is that all of this hydrogen, the excess concentration of hydrogen ions, is going to help run this ATP synthase, which brings out ATP. So there's going to be ADP from the Calvin cycle that already is there, along with some phosphate. So the H plus that goes through the ATP synthase provides enough energy for the ADP and phosphate group to combine together to make adenosine triphosphate, or ATP. So the NADP plus and comes from the Calvin cycle, and the NADPH comes, or it's going to go back to the Calvin cycle. The ADP and the phosphate group both come from the Calvin cycle, and the ATP is going to go back into the Calvin cycle. So the true reaction, if you want to call it, for photosynthesis, at least for the light-dependent reaction part, would be something like H2O plus NADP plus, which comes from the Calvin cycle, plus ADP plus phosphate group, PI. So that's all of this comes from the Calvin cycle, along with light. That's, let's say that sign right there, yields O2, which is getting out, along with NADPH and ATP. All right. So this is not the balanced chemical equation, but this is pretty much what happens throughout the light-dependent reactions. Anyway, let's do a quick review by answering these questions. So what are the products of the light reactions of photosynthesis that are utilized in Calvin cycle? Well, if we look at the equation that we just made, this one, we're going to notice that NADPH and ATP are the two products that we made during the light, right here, during the light-dependent reactions, which are going to be used for the Calvin cycle. So it's going to be NADPH and ATP. Remember, O2 is just a byproduct. It doesn't get used anytime. What is the relationship between light-independent and dark reactions? Well, they're both the same. Light-independent reactions and dark reactions are both the same. It's just another term for another. They're just synonyms. Let's see. Chemiosmosis translocate protons from where to where? All right, chemiosmosis is the process through which the electrons right here that go through the electron transport chain attracts the protons from the stroma, and it goes through the cytochrome complex into the thylakoid lumen. So it causes like a proton gradient. So it goes from the chloroplast stroma to the thylakoid lumen. Where in the chloroplast would the higher pH be during the light reactions? Well, during the light reactions, or during the light cycle, or light-dependent reactions, you're going to have higher pH. Remember, recall that we know that there's going to be more H plus ions in the thylakoid lumen than the stroma because of chemiosmosis. All of these H plus ions right here, or not all of them, at least a lot of them, are getting attracted back down into the thylakoid lumen, which henceforth creates a huge H plus gradient, or the huge proton gradient in the bottom or inside the lumen. Since pH is the negative log of the concentration of H plus ions, pH is equal to negative log of H plus ions. That would mean that there's a higher pH in the area with a smaller concentration of H plus. And that also means that the stroma of the chloroplast would have a higher pH than the pH of the thylakoid membrane. So what that means is whenever you have more H plus, you're going to have a lower pH because of this negative sign right here. In fact, the lumen becomes so acidic that it has a pH of almost 4, while the stroma is actually slightly basic with the pH of about 8. So the answer to this would be the stroma. Thank you for watching this video, and I hope you had a good understanding of the light-dependent reactions.